Okay, we're continuing our notes on slide 4. Okay, looking at equilibrium law and heterogeneous reactions. Okay, so again, heterogeneous reactions, there's just a change in state during at some point during the reaction. Okay. Pure solids or pure liquid often involve a situation that can be handled more easily by modifying the definition of equilibrium constant. Okay, so the concentration of a pure water substance does not change. So, like here with the liquid, because we have a liquid, the concentration of this liquid can't change. It's a liquid. It's not like we can change concentrations of gases, we can change concentrations of um, like aqueous solutions, things like that. But we assume that the equilibrium constant would be written like this. Okay, we use the prime as added to Kc to indicate that it's not the final equilibrium constant. So that's what we kind of do there. Is like if we were writing it out, we aren't quite sure. We write this little prime in, and then we just know like it's not our final statement. Okay, the concentration of pure water in the denominator of the expression never changes because it's constant. Okay, so it would be much more convenient to have one constant expression rather than two. So by convention, both sides of the expression are multiplied by the denominator to determine the commonly used constant Kc. So basically, we just take out our water because it stays constant, and because we're finding the equilibrium constant, we just take out that water. So in general, reactions with a pure solid or a pure liquid, when they're involved, their constant concentrations are not included in the concentration but become part of the equilibrium constant. So basically what it's saying is like if you have a liquid or a solid in your reaction, we don't include that in our Kc calculation. So this for this reaction, this is our equilibrium constant calculation. Okay, note that the concentration of pure gases can be changed because they are compressible, so their volumes can be changed. So the amount that's like in that area can be changed. Likewise, the concentration of dissolved solids can change during reaction, so that would be like in an aqueous solution. Okay, so here's a sample problem. So write the equilibrium law expression for the decomposition of solid ammonium chloride, and it's producing gaseous ammonia and gaseous hydrogen chloride. So again, step number 1, okay, is write your balanced chemical equation. So we have solid ammonium chloride. So ammonium NH4 1 plus, chloride Cl 1 minus. So that would be ammonium chloride. When we're doing a equilibrium equation, so we always do a double arrow. Again, it's producing ammonia, NH3. It says that that's a gas, plus gaseous hydrogen chloride, so HCl gas. Okay, we need to balance the equation. We have 1 nitrogen, 4 hydrogens, and 1 Cl, so it's balanced as is. Okay, so our expression, our equilibrium constant expression, Kc is equal to concentration of our products over reactants. Again, because this is a solid, we don't include it, so we're just going to have concentration of ammonia. Again, because there's a 1 here, we don't need anything here, times the concentration of hydrogen chloride. Okay, that would be our equilibrium or equilibrium law expression for this reaction. Okay, the next one, write the equilibrium law expression for the reaction of zinc in copper 2 chloride solution. So we have zinc solid plus copper 2 chloride, and that's in a solution. Okay, so our reaction, we're going to get zinc 2 chloride and copper. Okay, in our singular replacement reaction. Okay, again, it's all a 1-to-1 ratio again. Okay, we only, again, our zinc and copper solids, their concentration can't change. Okay, so the way we write it is our Kc is equal to our concentration of zinc chloride divided by our concentration of copper to chloride. Again, if we're given those numbers, we can then put it into this. We put those numbers in and actually solve for what the number is. Okay, so once we find our equilibrium constants, and we'll do some more examples with actual numbers, okay, we want to kind of know what those numbers represent. So the value of the equilibrium constants in a chemical reaction at specific temperature tells us kind of the extent of the reaction at that temperature. So how much reactants will actually produce the products. If our Kc, it just says K, but it should be Kc for all of these. Okay, so if our Kc, our equilibrium constant, is greater than 1, then the products are favored. So that means the equilibrium lies a little bit to the right. It's going to produce more products than it would reactants that are going to be left over. Some reactions where our equilibrium constant is greater than 10 to the power of 10, okay, these are regarded as proceeding completely, so quantitative. So the assumption we've always made is everything's quantitative, but really it's only if our Kc value is greater than 10 to the power of 10, then all of the product is being used up, or all of the reactant is used up to produce the product. Okay, when our Kc is around 1, then there's approximately equal concentrations of reactants and products at equilibrium. And if our Kc is less than 1, okay, then the reactants are favored, okay, which means our equilibrium lies a little or to the left. And again, kind of opposite of this one here, if it's smaller than 10 to the minus 10, then basically we're saying nothing is happening. You put those reactants together, nothing would happen in those cases. All right, so let's do some examples. So we have a mixture of nitrogen and chlorine gas is kept at a constant temperature in the 5-liter reaction flask. So they're all gases, so we can include them all in our reaction. Okay, when the equilibrium mixture was analyzed, okay, it was found to contain 0.0070 moles of nitrogen, 0.0020 moles of chloride, and 0.95 moles of nitrogen trichloride. Calculate the equilibrium constant for the reaction. So we want to write what is our expression. So like what is the formula we're going to be using. So we're going to have our products. So NCl3. We're going to square that because of the coefficient here. And then it's over our reactants. So N2, there's only one of those. Okay, and then Cl2, there's 3 of those, so we're going to put that there. Okay, so again, these square brackets mean concentration, so we need to find the concentration for each of these. So the concentration for NCl3 is going to be, again, concentration, C is equal to N over V. We have our N value and we have our V value, so we have to find that. So we're given 0.95 moles divided by 5 liters. Okay, so just make sure, don't just use these numbers in here. These are moles. We need to find concentration. Okay, so I'll type that into our calculator and get the answer. Okay, and our concentration, 0.19 moles per liter. Okay, our concentration of nitrogen, 0.0070 moles divided by 5 liters. 0.0014 moles per liter, and then chlorine, we'll round it 4.4 times 10 to the -4. I guess not round it, but put it in scientific notation. Okay, now we put those numbers into our equilibrium law. So we got here, I guess 0.19 squared over 0.0014 times 4.4 times 10 to the -4 and that will give us our equilibrium constant. For our answer, for significant digits, we have 2, so we're going to go 3.0 times 10 to the positive 11. Again, there's no units on our Kc value. It's a constant, and it kind of just tells us how it's proceeding. So now we look up here, so it's greater than 10 to the 10. And so basically it's saying all of these reactants are producing the product. Okay, we'll do this next example. So a technician places an amount of colorless N2O4 into a flask. He closed the flask and allowed it to proceed to equilibrium. The N2O4 partially decomposed to form a brown colored NO2. Okay, so we have our initial and final concentrations of both. Okay, what is the balanced chemical equation and the Kc? So again, our chemical equation, so we have N2O4 gas, and that is producing NO2 gas, so NO2. Okay, we need to balance it, so we just need a 2 here. Okay, so our Kc is going to be NO2 squared over N2O4. Put our numbers in. Okay, the only numbers we need are the numbers at equilibrium. Okay, those are the concentrations we put in. It doesn't matter what it initially started with. Okay, for right now, we'll use that more when we learn this next, like the ice tables on Wednesday. Okay, but right now, so we got 0.180 squared over 610. Okay, and so our answer, we got 0.053, we got 3 significants, right? 531. Okay, and then our last example here, calculate the Kc given the following information. So we have hydrogen and iodine gas form gaseous hydrogen iodide. So we have our volume of our flask is 2 liters, and then we have each of our moles. So we have to write out our balanced chemical equation. So we have hydrogen plus iodide, or iodine gas, and it's producing hydrogen iodide gas. Okay, so now we need to balance it, so we need a 2 here. Other than that, I think everything's set. Okay, we need to find out, and these are all in millimoles. Because they're all in millimoles, we can just divide them all by 2 liters, and we'll get millimoles per liter, but because they're all the same, they'll cancel each other out. Okay, and then, so our Kc value, we'll get Hi squared over H times I2. Okay, put our numbers in. Okay, so just once we've divided these all out, we all get millimoles per liter, and then we'll put our answer in once we put that into our calculator. 5.7, and for significant digits we got 3, so 5.71. All right, those are some examples, so that hopefully is enough to help you with your assignment 3.1. Again, let me know if you have any questions. Feel free to email me, or then we can work it out.